What happens when a mathematical space casts a reflection of itself, and that reflection casts another reflection? In some of the most elegant structures in mathematics, that second reflection perfectly recreates the original geometry. This raises a precise question. Can we learn more about a space by studying the continuous functions that operate on it, rather than studying the individual points themselves? When this double mirroring process returns us exactly to where we started, we call the space reflexive. Understanding this double-dual phenomenon gives us a rigorous test to determine whether an infinite-dimensional space is mathematically stable or wildly unpredictable. We start with a normed space X. Its dual space, denoted X', is the Banach space consisting of all bounded linear functionals that act on X. We can visualize this as a functional, f, evaluating a vector, x. This entire construction relies on the Hahn-Banach theorem. It ensures that the dual space always contains enough continuous linear functionals to fully capture the geometry of our original space. And as we establish mappings between different spaces, the corresponding adjoint operators naturally reverse the direction of the mapping between their dual spaces. Now, we are going to apply that exact same operation a second time. We will take the dual of the dual to construct the bidual space. To do this, we must invert our perspective. Instead of evaluating points, we have to evaluate the evaluators themselves. Here is the traditional way we think about evaluation. On the left side, we have the standard formula, f of x. The functional f is the active operator, absorbing a fixed vector x to output a scalar. But on the right, holding x fixed transforms the vector into an active operator itself, denoted as g sub x. Every single vector in our original space inherently defines a linear functional that operates on the dual space through this shift in perspective. This defines the second dual space, or the bidual, denoted x double prime. It is the complete space of all bounded linear functionals acting on x prime. We now have a complete three-tier architecture: space X, its dual space X', and the bidual space X double prime. Formalized by Hahn and Banach, these structures were later codified by Erwin Kreyszig in his textbooks at institutions like the University of Graz. By treating evaluation as a function of the operator rather than the vector, we have mathematically derived an entirely new geometric space out of our original vectors. To connect our original space to this new bidual space, we use the canonical embedding map, denoted by C. The mapping mechanism is direct. C takes a starting vector x and assigns it specifically to the evaluation functional g sub x. This leads to a rigorous geometric question, detailed in Kreyszig's lemma 4.6-2. Does this canonical mapping preserve the norm, or the size, of our original vector? The Hahn-Banach theorem provides the mathematical proof. It guarantees that the norm of g sub x inside the bidual space is strictly equal to the norm of the original vector x in the starting space. Because no structural length is lost during translation across these spaces, we classify this mapping as an isometry. Since it preserves length, the mapping is inherently injective. It is a one-to-one translation. We have proven that the original space will always embed into the bidual space without any distortion. However, we have not yet proven if the original space is large enough to fill the entirety of the bidual. There is a geometric difference between embedding inside a space and mapping completely onto it.
The image of our space C of x lands inside the bidual's boundaries, leaving an empty gap. Do functional elements exist in the bidual space that don't originate from X? This leads to definition 4.6-3. A space is reflexive if the canonical mapping is strictly surjective, meaning C of X perfectly equals X double prime. Reflexivity demands strict equality. Every single element within the bidual must be a simple evaluation functional generated directly by the original space. Notice the notation carefully. A common error is confusing the continuous dual space, denoted by a prime, with the algebraic dual space, denoted by an asterisk. They are strictly different objects in infinite dimensions. Furthermore, simply knowing that x and x double prime are isomorphic is insufficient. Reflexivity demands that the canonical mapping itself is the operator providing the surjectivity.
A reflexive space generates absolutely all of the bounded linear functionals on its own dual, without leaking any abstract geometry into the Bidual. Let's apply this to known geometries. Theorem 4.6-5 states that all finite-dimensional spaces are universally reflexive. Finite dimensions are mathematically contained. Because the dimensions match perfectly across mappings, basic linear algebra and rank nullity rules guarantee surjectivity. As we step into infinite dimensions, Hilbert spaces maintain perfect reflexivity. When applying the Ries representation theorem twice, conjugate linear mappings cancel out. The space flips, then flips back, landing perfectly onto itself. The little LP sequence spaces, for values of p strictly between 1 and infinity, operate similarly. They map to LQ and then reflect right back to LP. But here is where the structure fractures. All reflexive spaces are Banach spaces, but the reverse is not true. Not all Banach spaces are inherently reflexive.
Consider the sequence space C0, which consists of sequences decaying to 0. Its first continuous dual space is little L1, the space of absolutely summable sequences. If we take the dual of little L1, the Bidual space is little L infinity. The dimensions do not align. The original space C0 is merely a restricted subset floating inside L infinity. In extreme infinite dimensional environments, the Bidual mutates into a massively larger space. This mutation permanently shatters the perfect mirror of reflexivity. This tells us why reflexivity matters. It defines the point where a space's geometry is fully captured by its dual, ensuring predictability in infinite dimensions. In fields like mathematical optimization, reflexive spaces guarantee that bounded sequences always contain weakly convergent subsequences. This is the Banach-Alleglau theorem in action. This guarantee ensures that minimizers actually exist for complex systems in the calculus of variations and when solving partial differential equations within Sobolev spaces. Operator theory also relies on reflexivity to predict the behavior of adjoint operators without having to account for unexpected spatial leakage. Identifying a space as reflexive proves that it is structurally sound. Mathematicians can apply their standard geometric intuition without the risk of infinite dimensional anomalies ruining their models. If you want complete explanations of advanced mathematics textbooks, please like this video, subscribe to the channel, and share it with your colleagues. Let us know in the comments below which specific theorem, proof, or chapter you want us to cover next. Next, we will explore how reflexivity influences convergence and compactness in modern functional analysis.